Okay, so we are in section 9.3, and our key here is to know one diagram and its implications very well. Our diagram consists of a right triangle with an altitude drawn to the hypotenuse. And we've got to see in this right triangle with an altitude drawn to the hypotenuse that we have three similar triangles. And how do we see that? Well, we note that the whole triangle and this triangle, the larger of the small two, share an angle, and they each have a right angle. Ditto with this small triangle and the whole triangle. Those two triangles share an angle, and they each have a right angle. So finally, if both of the two smaller triangles formed by the altitude are similar to the big triangle, then those two triangles will be similar. And the key is making sure that you set up your ratios of corresponding sides equivalently. So let's go on. Okay, so in our right triangle with an altitude drawn to the hypotenuse, we have certainly sides in our original triangle, and we'll call the large triangle's hypotenuse. We're going to set that up into two lengths, x and y, and we'll call the altitude's length t. So if I set up these ratios properly, let's just look at the ratio of the small triangle to the whole large triangle. If that's true, then x over t, that's, for example, the small leg to the large leg, equals a over b, which then will equal also, for example, hypotenuse to hypotenuse, which would be a over x plus y. So again, you might want to draw out the triangle separately, and that way you can see things better. So I've got my x, my t, and my a, and in the large triangle I've got my a and my b and my x plus y. So drawing them out might help you see things. And again, I can set up those ratios also, certainly as x to a equals a to x plus y equals t to a. So again, just make sure you set up your ratios properly. Okay, so in this setup, again, what we're looking at is we have our right triangle with the altitude drawn to the hypotenuse, and we set up ratios of corresponding sides. In this case, I've used the small triangle in the upper left to the whole triangle, and so leg to hypotenuse equals leg to hypotenuse. So S over W equals W over S plus T. Means extremes product theorem then gives me W squared equals S times S plus T. And that, you'll note, is I certainly, if I go backwards now, I've got W as a geometric mean in between. The question is how to describe this S and S plus T. Well, S is the length of the segment closest on the large hypotenuse to this leg W times the whole hypotenuse. I'll say that again. The leg in the large right triangle is the geometric mean between the segment on the leg closest to the hypotenuse times the whole hypotenuse. Now, do I need to memorize this formula? No. I certainly can see the similar triangles, set up my ratio of corresponding sides, and derive it each time. The issue with that, though, is note I've used two of the three ratios. If you're going to derive it every time, it might take you looking at all three ratios and recognizing where you're going to get the W as either means or extremes to set up your cross multiplication. So I recommend keeping track of the pattern. Once again, the pattern, leg squared equals segment on hypotenuse closest to leg times whole hypotenuse. Okay, again, our patterns that we want to keep track of from those similar triangles are as follows. Each leg in the large triangle is the geometric mean between, for example, for D, the segment closest to that leg in the hypotenuse times the whole hypotenuse. So therefore, D squared equals E times E plus F. Ditto, I've got certainly the same issue. If I can do it with leg D, I can do it with leg H as well. So therefore I'm looking at H squared equals segment closest to H on the hypotenuse is F times E plus F. And finally, the third formula you want to keep track in this figure is actually the easiest. I think it's the T formula, if you will, and that is G squared equals segment on hypotenuse times segment on hypotenuse. So from the previous slide, we've showed that in each case, the leg of my right triangle, each leg is the geometric mean between the segment on the leg closest to the segment on the hypotenuse closest to the leg times the whole hypotenuse. So if I then go ahead and add equal things to equal things, I get D squared plus H squared equals E times E plus F times E plus F. And then we've got to do a little bit of Algebra 1, factor an E plus F out of each expression here on the right, and I get E plus F factored out times what's left. What's left is an E plus an F. And we note that E plus F is, E plus F times E plus F is E plus F quantity squared, which is the hypotenuse, you'll remember, in our original triangle. So we've showed that D squared plus H squared equals E plus F squared, or certainly this is one proof, if you will, of the Pythagorean theorem.